Okay, so now for differential equations. We may sometimes have to find an original function given information about its derivative. An equation that involves the derivatives of a function is called a differential equation. So, number 10, we want to find f of x, and we're given that f prime of x is equal to x root x, and f of 1 is equal to 2. So, I want to start off with the derivative and find the original function. And to get from the derivative to the original function, I need to take the antiderivative. Then we'll deal with this f of 1 equals 2. We'll see what that helps us out with. So before I do anything, let me rearrange this x square root of x. Let me write this a little bit differently. I'm going to write this as f prime of x is equal to, well, this is kind of like x times the square root of x is x to the power of 1/2. And I know that when I multiply like bases, I add those exponents. So this is really x to the power of 1 times x to the power of 1/2, or x to the power of 3/2. Okay, now let's take that antiderivative. So now I'm taking the antiderivative to get to the original function. So now I've got f of x is equal to, I know that my power rule for antiderivatives is that I'm taking this base, I'm adding 1 to that power. So 3/2 plus 1 is going to be 5/2. And I'm dividing by that new power of 5/2. I remember I have that plus c on the end of each antiderivative. Now let me clean this up a little bit. I've got f of x is equal to, dividing by 5/2 is the same as multiplying by 2/5. So I've got f of x equals 2/5 x to the power of 5/2 plus c. So now what do I do with this f of 1 equals 2? Well, this is going to give me my constant. So if I plug in 1, so if I find f of 1, I'm going to be left with 2/5. Well, this is just going to be 1 to the power of 5/2 plus c. And my initial condition, this is what's called that initial condition here. This is called my initial condition. My initial condition tells me that this is equal to 2. So it tells me that this is equal to 2. So this will allow me to solve for c. All right, so let's do that. 2/5 times 1 times to the power of 5/2. Well, this is just 2/5 plus c equals 2. Well, I can bring this 2/5 to the other side if I subtract 2/5 from both sides. Okay, well, this is going to leave me with c equals, well, 2 is really kind of like 10/5. 10/5 minus 2/5 is 8/5. So my c is 8/5. And so finally, I can write my original function as f of x, equals 2/5 x to the power of 5/2 plus 8/5. This is going to be my final answer. So that's what I'm doing with this differential equation, is that we're still finding the antiderivative, but then instead of finding the most general form of the antiderivative, I'm actually solving for that c using the initial condition. Let's do one more example of this. Notice in this next example that we're given the second derivative of f of x, and that's equal to x squared. And then we're given two initial conditions. So I'm going to need to just work my way backwards to solve for now two constants that I'm going to get by finding that antiderivative. And so let's start off to get from the second derivative to the first derivative, I need to take the antiderivative. So my first derivative, f prime of x, is going to be, well, I know that I'm taking this x squared, I'm adding 1 to this power, so this is going to be an x cubed, and I'm dividing by that new power. Okay, and of course I've got that plus c. So now for my first initial condition, f prime of 0 is equal to 3. So I can find f prime of 0. This is going to be 0 cubed over 3 plus c, and I have that this must be equal to 3. All right, so let's solve this equation. 0 cubed over 3 is 0, and I have 0 plus c equals 3. Well, that really just means that c equals 3. So this is my first constant. And so now I have to rewrite this derivative, and I get that f prime of x is equal to x cubed over 3 plus 3. So now I've got my first derivative of this function, but remember my goal is to find the original function. So now I'm going to go back up here, let me move up here, and now I'm going to run it again. So now I'm going to go from the first derivative to the original function by finding the antiderivative. And so using that same power rule, this is going to give me f of x. Now finding that antiderivative is equal to, and I'm going to add 1 to that power, that's going to make this an x to the 4th power, and I'm going to divide by that new power. So now I'm dividing by, well, I'm going to multiply that by the 3 that's already in the denominator to give me a new denominator of 12. Now I can't forget about that plus 3, and I remember that the antiderivative of plus 3 is plus 3x. End up multiplying that 3 by an x. Okay, and then I've got another, now I can call this a plus c, but because I already use c, sometimes we'll call it a plus d. Just a different letter for a constant. Okay, now I've got one more initial condition that can help me solve for d. I've got that f of 1 is equal to 1 to the 4th power. Let's clean that up a little bit. That's 1 to the 4th power divided by 12 plus 3 times 1 plus d, and I have that this must be equal to 4. All right, so now 1 to the 4th, well, that's still 1, so that's going to be 1/12 plus 3 plus d equals 4. Well, let's get everything to have a common denominator here. This is, well, 1/12 plus 3, so 1/12 plus 36/12 plus d equals 48/12. All right, combining these terms on the left, I get 37/12 plus d equals 48/12. And finally, subtracting 37/12 from both sides, I get that d is equal to 11/12. And finally, now I have that last constant, and so I can write my final equation, f of x equals x to the 4th power over 12, or 1/12 x to the 4th power, plus 3x plus 11/12. So this is my initial function, given my second derivative and my two initial conditions. And so that's our process of solving a basic differential equation.